And there's the final review question and answer session, which will be over the weekend, which will also include pizza, and I highly recommend attending. So I think we're still figuring out the logistics for that, but we'll email you when we have more details. Right, so any general questions before we get started today? No? Okay, so today's topic is, it's a little bit, it departs from the realm of sort of traditional computer architecture that we've been looking at throughout the course, and it kind of goes down the path of more exploratory or emerging memory technologies. So today we'll be talking about these new emerging memory technologies that are being already integrated into some systems, and some of the challenges that we have when we're trying to use them, and some of the benefits that they can provide. This is a topic that's especially near and dear to me because I do a lot of research in this area. So, as always, feel free to ask questions. I can go into a lot more depth. Cool. So let's start at the high level, like we always do, with where does memory even come into play within systems? So as you're all aware, we have processors and caches, lots of them. And we have storage that's persistent, where we store all of our data and files. And memory is the thing that sort of acts as the mediator between these different devices. Now, it's a critical component in all types of computing systems. It doesn't matter whether you're looking at a server, whether you're looking at your desktop, whether you're looking at a tiny little embedded device that's being, scattered out across oil fields somewhere halfway across the world. Memory plays a really important role. And main memory systems have to scale. They have to scale to meet the demand of larger numbers of cores, larger caches, larger disk space that needs to be buffered. So they need to scale in terms of size, in terms of technology, so the actual size of the cells that are storing data, efficiency, cost, and the way that we manage them. And this is to maintain performance growth and technology scaling benefits that are provided by the other devices in the system. If memory doesn't scale, then eventually it's going to become a bottleneck, and it doesn't matter if we improve the performance or capacity of these other devices. So here's sort of the president gives the State of the Union address. I'm going to give you a one-slide state of the main memory system address. And I guess the outlook at first is kind of grim, so let's take a walk through this. So if we look at what's happening in recent just technology trends, recent processor trends, recent scaling trends, we see that there's new requirements that the memory system needs to provide, and we'll go over some of those. And also, there's exacerbated old requirements that the memory system used to be able to provide adequately. And we'll take a look at some of those as well. What we'll see is that DRAM alone, just using DRAM in systems, it's going to be unlikely to satisfy all of the requirements that we have for future systems. And so some emerging non-volatile memory technologies, and we'll focus on one in this talk, PCM or phase change memory, appear to be promising to satisfy the new requirements for systems. And they enable new opportunities as well. So the main thing is we need to start rethinking about what we mean when we talk about a main memory system. In the future, it's probably not going to be entirely DRAM. It's going to be composed of a bunch of different devices. How do we manage those? So first, we want to fix the issues that already exist with DRAM memory and enable new emerging technologies that have other benefits. And we also, at the same time, want to satisfy new requirements and the exacerbated old requirements. So here's the outline for what I'll be talking about today. It's just going to be a quick overview of the challenges and benefits of these new technologies. We'll talk about some major trends that are affecting main memory, requirements from an ideal memory system. If we didn't have technology constraints, what would we like to do? And then I'll talk about one really interesting opportunity for future memory systems, which is emerging memory technologies. OK, so what are some major trends that are affecting main memory? Well, here's some. Obviously, maybe not obviously, but hopefully for you guys it's obvious that we need to keep increasing main memory capacity and bandwidth. And this is for several reasons, which you could probably already guess. In addition, Main memory energy and power is a key system design concern. Remember DRAM, dynamic RAM? You have to keep refreshing it all the time. Maybe DRAM doesn't really make sense when you have a little wireless sensor that's deployed somewhere, and most of the time you just need to refresh its memory to keep it operational and running. You'd like something that you didn't have to spend that power on. And DRAM technology scaling is ending. So just like there's Moore's law, which predicts that processors will increasingly be able to store more and more transistors on them, for a long time previously, DRAM kept scaling and scaling and scaling. We kept making capacitors smaller and smaller and smaller and doing different things with them, turning them different directions. But that's coming to an end, and the industry leaders are all in agreement on this point. And so we need to start looking at other technologies that we can substitute or maybe even use to improve upon DRAM. So why is memory capacity in such high demand? Well, I alluded to this earlier, but as we've been talking about, we're starting to see more and more and more cores on each chip. And we're seeing more and more concurrency among the threads that are running on these cores. And in addition, larger working sets that these threads are accessing. Remember we talked about working sets? It's all of the data that you touch within a certain amount of time. So we're starting to see all of these three trends. And what does that mean? That means that, first of all, these emerging applications that are really important are very data intensive. Okay, but that itself isn't too much of a problem. The problem is when we try and run these really data intensive applications on machines that share memory among all of the different threads, we could run into some problems. So where are some cases where this might be interesting? Well, cloud computing, right? What's the idea behind cloud computing? You have a huge server farm, and you want to run people's virtual machines or just whatever independent tasks they have. They can rent resources from you. Maybe they pay by capacity or bandwidth or time. And your job as the cloud service provider is to group these things onto machines, make sure that they run efficiently, and you can make a large profit from this. Well, when you start consolidating these different applications onto smaller numbers of machines, they're going to have a really high memory demand per machine. We need to satisfy that. GPUs. So when you're running a game or if you're running some sort of GPU-intensive application, you're typically loading a lot of data from memory in a small amount of time. Think of all the textures that you have to load to be rendered onto different planes in the game. Those textures aren't really small. They do tricks to compress them, but there's only so much you can do if you want to have a very diverse environment. We need lots of memory bandwidth there. In the mobile realm, so if you have this type of consolidation where maybe you're using some devices at one point in time, or you're offloading computation to other devices, if it's sort of a peer-to-peer mobile application, there could be reasons why you want a lot more memory there. Why can't we satisfy this demand? Well, let's take a look at sort of what the trend has been showing us. So as we talked about, core count has been roughly doubling every couple of years. That's good. That means we can fit a lot more processes on the same unit of area on a chip. Here's the problem. DRAM DIMM capacity, dual inline memory module, has been doubling every 3 years. Now this doesn't sound like that big of a gap, but if you start to plot the trend, and if you start to sort of see what's going to happen and project that into the future, the amount of memory capacity that we have per core is expected to drop by 30% every 2 years. So the rate at which we're adding cores that need a lot of memory to the system can't keep up with the rate that we can add more memory to the system. And furthermore, those cores are actually running programs now that are really, really data intensive compared to in the past. So this is a really big problem. We need to try and find ways to address this. Right, so at a high level, we need a lot more main memory capacity and bandwidth because we have multi-core systems, because we have these data-intensive applications, and because we have consolidation, putting multiple applications on the same machine. In addition, if it was just about capacity, maybe we could just buy more DIMMs, maybe we could put more DIMMs on the system. The problem is it's not just about capacity. We also have energy and power that are really big design concerns for these systems. So this is a relatively old study from 2003. There might be more up-to-date ones. But one data point, just to give you an example, is that some IBM servers had about 50% of their total system energy. So now we're talking, you have a server box, you plug it into a power meter, and you have some way of measuring how much power is drawn by the memory subsystem. You can measure that. About 50% of the total server energy was spent just on main memory. That's huge, especially when you start to consider the fact that we're seeing Google and Facebook with server warehouses that have thousands of machines. That's a lot of money, right? Also, in addition to just that, DRAM consumes power even when it's idle. Remember, we have to refresh it. And that can be a problem as well, especially if we're not really using that memory that intensively. Maybe we don't want to refresh all of the memory. Maybe we'd like to just refresh a small portion of it, or maybe none at all. And like we talked about before, DRAM technology scaling, we believe, is approaching its limits. So the ITRS, which is this industry consortium, it's a bunch of companies that get together and sort of talk about like what are the future of different memory devices and storage devices. They predict that DRAM won't easily scale below 40 nanometers. Now, maybe that particular figure doesn't really make much sense, but let me put it into perspective. They believe that in the next few years, the way they put it is there don't currently exist like technological ways of fabricating DRAM that goes below that capacity. So we're going to start to hit this wall relatively soon. And this is a problem because scaling has provided, traditionally, lots of benefits for system designs. Higher capacity, higher density, lower cost, lower energy. It almost seemed too good to be true. Every couple of years when you went to buy more DRAM, it was magically faster, cheaper, and you could buy more of it than before. But we're running into a wall there. So what's the fundamental problem that's limiting DRAM scaling? Well, we're going to need to go down to the little tiny cells that make up the device to be able to look at this. And I'll just give a high-level overview. So as we've talked about before, DRAM stores charge in a capacitor. That's how it stores information. It's called a charge-based memory. We'll contrast this with a different type of memory soon. So the capacitor that it stores the charge in has to be large enough to allow reliable sensing. If it's too tiny, then maybe the charge will leak out. Or if we try and sense it, it will just perturb the signal very barely, and we can't even sense it correctly with some sort of like analog to digital converter, for example. And there's this thing called an access transistor that connects it to certain wires in the system. And that needs to be large enough to have low leakage and high retention time. So this means we don't want to refresh these cells all of the time. We need something that sort of blocks off the charge from leaking, right? And so scaling beyond some current technology nodes can be really challenging, okay? Now, the fundamental reason is just because it's hard to make capacitors that small that are reliable and that don't leak very well, don't leak a lot. So it's hard to scale capacity, cost, and energy and power going into the future. So what are some problems that might be posed when DRAM's used as main memory? Okay, so we need a lot of memory capacity and bandwidth. We've went over some of the reasons why this is the case. But DRAM capacity is hard to scale. Darn. Looks like we have a problem there. Memory, energy, and power is a key system design concern, like we talked about, but DRAM consumes really high power due to leakage and refresh. That's not very good. We might want to look at something else. Also, DRAM technology scaling is ending. That's sort of the thing that sort of puts the final nail in the coffin, right? Even if we could put up with capacity, bandwidth, energy, and everything else, we're nearing the end of DRAM scaling. So we're not going to see those benefits as much going into the future. Okay, so those are some trends. I hope by this point I've sort of motivated why we might want to start looking at different technologies to use in main memory. And right now what I'm going to do is I'm going to talk about some requirements from an ideal memory system. If we could architect the perfect memory system, what might it look like? Okay, so some of the traditional concerns that we've that architects have always wanted from an ideal memory system have been enough capacity, where enough is enough for the working set of your applications, for example. Low cost, remember, or maybe not remember, but I'll bring this up as a point. DRAM is a very cost-driven industry. So servers need a lot of DRAM, therefore the cost per chip needs to be really low. Also, fabrication techniques for DRAM need to be very, very reliable. You need to have a really high yield, so you don't have to throw away a lot of chips and increase the cost of your product. That's another concern. And ultimately, we want really high system performance. So we want high bandwidth, low latency. But there's some new concerns that are starting to emerge in future systems. So for example, we want technology scalability. We want the actual cells themselves to be able to scale really well going into the future, not just hit some sort of roadblock and not be able to do that. We have energy and power efficiency that haven't been traditional concerns for a lot of different companies and things like that. And quality of service support and configurability. So what does this mean? This means that if we're doing consolidation, remember, if I'm running my workloads in the cloud and you're running your workloads in the cloud, I don't want your workloads to hog all of the memory resources. I don't want you to run MATLAB and me to run GCC, and my GCC program takes a lot longer to run. I pay a lot more money, but the reason was because your MATLAB program was hogging all the memory resources. We want this configurable so that we can tune the way that fairness is handled in these systems. OK, so those traditional concerns are also very important. So here are a couple of things, just to sort of give you a preview, that emerging technologies can help. And we'll talk about these. They can have higher capacity and continuous low cost, meaning they're still able to scale, they project, very favorably into the future. In addition, so they have this whole technology cost, scalability, higher capacity, and they can have better energy efficiency than traditional DRAM devices. So let's take a look at why some of these might occur. So let's look at the opportunity here to fit emerging memory technologies into the memory hierarchy. OK, so a lot of people have thought about this problem for a while. They've looked at the different alternatives. And it seems like it's likely that we will replace or augment DRAM in its current sort of location in the memory hierarchy in existing systems. And we want to ideally replace it with a technology that's scalable. So we want to be able to keep increasing capacity into the future. And also one that's at least similarly efficient. We don't want to make this trade-off for capacity for a device that gives us a bunch more capacity, but it's really, really slow. If that were just the case, we would just use disk or something like that, right? We need something that's comparable to DRAM, or as close as we can get. And the key thing here, and what I'll talk about a little bit later on, is the underlying cells themselves don't have to be as fast or as energy efficient as DRAM. This is an important point. We don't have to design the physical properties of the cells to be like DRAM. Remember, we're the architects. We can take all of the components in the system as building blocks, put them together, and design a system that can be as efficient as an all DRAM system. So we can take an inferior technology compared to DRAM, do a couple of things to sort of patch up its inefficiencies, and make it as efficient as an all DRAM system. And I'll talk about a couple of directions that we've been looking into along those lines. So there are a few different emerging technologies, and we call them emerging. I guess now they're a little bit more mature. For example, if you look at phase change memory, this is one promising technology. In fact, I think a lot of actually Samsung phones have phase change memory in the device. It's a non-volatile RAM that's basically used to store some phone setting information. I think PlayStation 3s even have some phase change memory in them. So we're starting to see some of those integrated into devices. One that's a little bit more experimental at this point is something called spin torque transfer magnetic memory. I won't be talking about this one as much, but this is just another storage technique that stores data in a different way from PCM, but has similar properties. Memristors, these are some really cool devices that were developed at Hewlett-Packard Labs. And basically what they do is they store data in the form of resistance. So think about a resistor, but now your resistor isn't constant. If you pass current one way across the resistor, it increases resistance up until some threshold. If you pass current the other way across the resistor, it decreases resistance down to some lower threshold. That's really cool because if we can build the devices to actually sense what the resistance in these memristors are, we can build a really scalable storage technology. In addition, what does that kind of sound like? Sounds like something from biological sciences, actually. Anybody have a guess? So you can actually build some interesting neural networks out of these devices as well, right? It kind of operates how biologists have sort of abstracted the function of a neuron, the way that those operate. So people have been looking into that as well with these. And there could be a lot of other ones. So I'll talk about one specific one. But really, the techniques that we're trying to develop for these systems shouldn't rely solely on just phase change memory or memristors. Really, what we're just looking at is a slower memory technology compared to DRAM that has some different characteristics, and all of these kind of fall into a similar category. And the key question that we want to try and answer is, can they be enabled to replace or augment or even do better than DRAM? Let's take a look. So just to give you, okay, I've talked about the memories at a relatively high level so far. Phase change memory, memristors, DRAM. Let's sort of dive down just a little bit into what actually makes up these new emerging memory devices and what makes them really cool. So here's the key distinction that I'd like to draw between traditional memory devices and these emerging memory devices. And it's really one of charge storage versus resistant storage. So charge-based memories, like DRAM or flash, write data to a device, to a cell, by capturing a certain charge. Let's call it Q. And they read data from a cell by detecting voltage, V. Resistive memories, in contrast, these are like the ones we've been talking about, they write data by pulsing a current. So they pulse some current for some amount of time, and that actually modifies the physical state of the cell itself. And we'll see a more detailed example. And they read data by detecting the resistance of that changed state of the cell. Okay, so what are some limits of charge-based memory? We kind of alluded to these before. So it's difficult to change, it's difficult to charge for charge placement and control. So it's difficult to actually get the charge to stay in one place and read it reliably as cells get smaller and smaller. So in flash, we see this with a floating gate that technology has. In DRAM, this is because of the capacitors and the fact that charge can leak out through the access transistor. And so reliable sensing becomes really difficult as the charge storage unit's size reduces. Even if we could ideally refresh these devices, there can still be physical effects that could cause basically inconsistencies in the way that we're reading data from these devices after we store it. So this is a big problem. And emerging resistive technologies operate in slightly different ways. So let's take a quick look. Phase change memory, or PCM, injects current to change the phase of the material that actually makes up the cell. And the resistance is determined by the phase of that material. We'll look at some pictures in a second. Spin transfer torque MRAM injects current to change the magnetic polarity of the device junction. And the resistance is determined by the polarity. So those are related. Memristors, like we talked about, inject current to change the atomic structure of that resistive substrate. And resistance is determined by the atom distance from different threshold barriers. We won't go into too much detail on STT-MRAM or memristors, but we'll take a look at PCM right now. So interestingly enough, you've probably used a lot of phase change memory in your life in the form of CD-ROM drives. So CD-ROM drives, they're kind of like shiny and mesmerizing to look at. what you're actually looking at the bottom of those is chalcogenide glass. And the glass exists in two different states that are easy to control. One is the amorphous state, which has low optical reflexivity and high electrical resistivity, and the crystalline state, which has high optical reflexivity and low electrical resistivity. So obviously, we use the optical properties for optical media, like CD-ROMs and DVD drives. We can shine a laser onto this, this material, and we can see how it refracts through the device. And we use the resistance properties for storing data in a storage medium. OK, so here are a couple of pictures of what the actual device looks like. To change the phase of these, we actually have to heat up the material. So we can use a very powerful laser to do that, or we can actually use a wire that's just up against the material itself, and we can send a bunch of current through that wire. And as long as the sort of the surface area of the wire touching the material is large enough, we can actually melt we can actually melt the material there and cause it to change its phase. So we typically encode binary values as high resistance is a 0 value, low resistance is a 1 value. And the point here is that we can switch between these two different values pretty quickly and pretty reliably, which makes it a great option for storage and memory. So how does it specifically work? Well, if we're doing a write operation, we basically, like I said, we change the phase of the material by injecting current into the device. So when we have a set operation, maybe we're setting it to 1, we'll apply a sustained current to heat the device above a certain threshold temperature. And that will actually cause the phase of the material to slowly change toward the one that stores the 1 value, right? And we can reset the device by heating it above another higher threshold that will actually melt the material. And if we quickly quench the device, if we quickly cool down the device, it'll harden back again into its original state. To read, we basically just have to send some current across the device and measure the resistance. So whether it's in one of these two phases, amorphous or crystalline. So what does this look like? Well, here's the set operation, which is the crystalline phase. It has the low resistance right here. So here's a couple of the junctions right here. We have a heater of something that we can use to sense. And this is basically the piece of material that's letting electrons pass through. In this picture, it doesn't look like it, but it's kind of wide. If we contrast it with the reset amorphous state that has a high resistance, you can see that it's actually tinier here. So it has a higher resistance. It's not going to let as many electrons through per unit time. And you can see that these resistances actually vary by orders of magnitude. This is an important property to have because it makes sensing the resistance a lot easier. We don't have to have as sensitive circuitry to sense the resistance. Cool. Phase change memory. What are the advantages? So what we've been talking about all along is we hope to have devices that can scale better than DRAM, and we believe that phase change memory can actually accomplish this, in fact surpassing DRAM and flash technology. So it requires current pulses to melt the devices or to heat them up, and these scale linearly with the feature size of the device, and it's expected to scale to 9 nanometers. Remember, DRAM could scale to 40 nanometers, so this is pushing that wall a lot further out. And people have actually prototyped these devices as far back as 2008, and even further than that, in fact, because remember CD-ROM. But here we're talking about specifically like memory type devices at IBM. So another benefit is that this can be a lot denser than DRAM because we can scale it smaller and smaller. So and in addition to being able to scale it smaller and smaller, because we're dealing with resistance now, we can actually, depending on how precisely we can measure resistance, we can potentially encode multiple bits in a single cell. We just have to sense the resistance at a finer granularity. And so people have built devices that store 2 bits per cell. Here's a big thing that non-volatile memory has that DRAM doesn't have. And it ties back to its name, right? It's non-volatile, so it can retain its data for a really long time. This is cool because it can actually be used like storage devices, except now that your disk drive is hundreds times faster, and we'll put that into perspective in a second. In addition, there's no refresh needed. So with DRAM, we had to constantly refresh these devices. It's non-volatile here in these memories. We don't have to worry about that source of energy. Cool. So there have been some studies that have looked at different prototype devices that have actually been made to try and figure out, so let me back up a second and preface this with, since we're architects and we're kind of working on the bleeding edge of system design, we don't have hardware prototypes necessarily that we can work on. That would be cool if we did, but even if we did, they might not have the properties that we expect them to have in, say, 5 or 10 years. So it's important to, when you're designing studies and when you study systems in whatever job that you end up taking, it's important for you to be able to have a good handle on what are parameters for whatever design that you're looking into that actually makes sense. And one great way of finding parameters is to look at what have people that have actually done similar things published, or what have they talked about, or what do press releases say, and sort of aggregate those numbers and figure out what are reasonable values to actually look at. So this is what one work that Professor Mutlu was on did a few years ago. They surveyed a bunch of different prototypes, and they came up with some parameters for phase change memory in this example at 90 nanometers that they thought were reasonable. And they did some studies based on those that we'll go over. Basically, what they found was that phase change memory, they expect to have latency that's comparable to, but slower than DRAM. What does that mean? That's kind of an oxymoron, right? But if you look at this graph here, along this line are logarithmically increasing latencies in terms of number of processor cycles to access these devices. On the left of this line is the fastest latency. On the right is the slowest latency. The fastest one goes to SRAM, right? Probably actually registers are over here somewhere. But yeah, level 1 cache, really fast, obviously. Then there's this eDRAM, which you may or may not have heard of. eDRAM is a different way of fabricating dynamic random access memory that gives it properties that are closer to SRAM. That's just another data point. Then that would typically be used as an on-chip cache. But then if you start to go off-chip, we're talking about main memory. We're talking about DRAM, and here's where phase change memory fits into the picture. So it's within a couple of orders of magnitude to 1 order of magnitude, depending on what particular access you're performing to the device. And then there's a really big gap between phase change memory and flash, and another really big gap between flash and hard drive. So I guess the way that I kind of think of it in my head is, if you were to replace the hard drive in your system with flash, that's kind of a similar improvement to if you replaced the flash in your system with PCM, for example, or you added PCM as another level in the memory hierarchy. It can be pretty big of a difference. OK, so what does this all, how does this all basically fit into the picture? Well, in terms of read latency, it can be about 4 times that of DRAM. Not too bad, considering its properties. And it's about 1,000th of the latency of flash. That's pretty good. In terms of write latency, it's about 12 times that of DRAM. Question, why is write latency so much longer than read latency in non-volatile memory compared to DRAM? You have to melt the thing, right? You actually have to, in some cases, you actually have to apply enough current to melt the device. Now, we talked about there's the set and reset operation, right? Reset is kind of, you give it this really big pulse of energy, and it melts the device, and we cool it very quickly. That actually doesn't take too long. It's the other operation that basically has to pulse a lower amount of energy, or basically the same amount of energy, but over a longer amount of time, that can actually become the bottleneck for the write operation, the one that slowly changes the phase to another resistance state. That could be a problem, but we'll look at some ways of dealing with that. In terms of write bandwidth, it's close to DRAM and basically similar to flash. OK, so it sounds like a pretty appealing device to look into. Here's some characteristics in terms of energy. 2x to 43x, that's a huge range, but yeah, sorry. Yes.
How quickly does it wear out? Because you are doing these melts and melts kind of thing, so I would imagine that it's not necessarily going to last forever.
We were almost there. So close, yeah. We'll talk about that right now. So in terms of dynamic energy, there's this huge range from 2x to 43x. The 43x there is mainly because of writing data, right? That takes a lot of energy to perform. OK, endurance, like Mike was pointing out, in DRAM, I mean, you're not changing the device itself. You're just changing the charge that's stored in it at any point in time. Here, we're melting, cooling, melting, cooling, melting, cooling. And if you've ever done this with some sort of material, occasionally it might break, right? It might fracture, it might crack. And if in phase change memory, if that junction there were to break or crack or just be changed in a really weird way, that destroys all of the resistance properties that we would be used to measuring. In fact, it might not even transfer current across that junction anymore. So here's the deal on endurance. It takes a lot of temperature to actually induce that phase change, 650 degrees Celsius. And the contacts between that material can actually degrade over time. The material can separate from them, which doesn't give us these desirable properties. So that study that I talked about that Professor Mutlu was on, when they did their survey of different devices at the time, what they came up with as a ballpark figure was around 10 to the 8 writes per cell. What does that even mean? Well, we'll take a look at what that means on some actual workloads and how long your system would last. But that's the actual figure that they came up with. If you look at different people that have made these devices, it can actually, it can vary. It has a very large range. But that's kind of the rough ballpark that we're looking at, right? Compare that with NAND flash, which is 10 to the 3. So it requires this intricate wear leveling, firmware, and other things, garbage collection, or DRAM, which is 10 to the 16. So we don't really think about DRAM like ever wearing out, but it actually can wear out over time. I mean, it's a physical device just like anything else. It's just it would take a really, 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 really long time before we could actually wear DRAM out. In fact, other components in the system would, in the DIMM itself would probably fail before the cells. OK, but the upshot, the silver lining, at least the silver lining from the device perspective, is that the cell size of phase change memory can be really, really small, which is good. That means higher capacity, larger main memories. So just to summarize, what are the pros and cons? Pros compared to DRAM is better technology scaling, non-volatility, which we haven't really talked about how that's much of a pro yet, but you can kind of imagine if you, well, one of the obvious reasons is you don't have to refresh it, but you can think of application level reasons why this is better than DRAM, because now say if you have some persistent data in your programs, you can, let me give a concrete example. If you're running a huge database program like MySQL, and you have some databases that are kind of tiny and you access them very frequently. Maybe you have some internet-facing server that's doing authentication for people logging into it, and you have some authentication database that you access all the time, thousands of times per second. Maybe you want that to stay persistent, because maybe people are changing their passwords and doing stuff like that, but you also want it to be accessed really, really quickly. Well, phase change memory is great for that. It can provide both of those benefits. And sort of coming off of that is the fact that it has low idle power, no refresh, like we talked about. The downsides that we'll try and mitigate in some designs is the higher latency, especially writes, higher active energy, especially writes, and lower endurance. Remember, cells can actually die within a reasonable, within a expected lifetime that we might actually see when we're using the device. So what are some challenges in using PCM and as a DRAM replacement or something to augment DRAM and main memory? Well, the first order of business is we want to mitigate these shortcomings. We want to design systems that are robust against those. And we want to find the right way to place it in the system. We haven't really talked about this yet, but if I gave you some phase change memory, and I said, how do you want to use it in the system? I mean, you could place it anywhere, right? We've kind of been talking it colloquially as it's near DRAM or it's in the main memory. But I mean, you could use it as a disk cache. You could use it even on chip as a large on-chip cache. And some people have proposed doing that. So there's a lot of different questions about where do we actually want to use phase change memory. And we also want to ensure secure and fault-tolerant PCM operation so that we don't just start randomly losing data. OK, what are some research challenges? So these have been sort of the technical side of phase change memory. Now we're going to transition into more of the exploratory side of how can we actually use these devices in systems. So one question that I talked about is where do we want to place it in the memory hierarchy? So I'm going to limit the discussion to just the main memory right now. We're not going to consider disk cache or on-chip cache, although those are also viable alternatives. So for example, one high-level approach might be maybe we have PCM and DRAM in main memory, but it's up to the operating system to determine where data is placed between these devices. Maybe you call NV malloc, and it allocates a page or some data on the non-volatile device, or you call malloc, and it allocates a page on DRAM. That's an option. We could have an OS-controlled phase change memory, so this is like traditional memory systems, but a hardware-controlled DRAM cache. So now DRAM is acting like a cache to phase change memory. When you call malloc, you get a page that's backed in phase change memory, but sometimes when you access that page, it goes a lot faster than other times because it was cached by the hardware in DRAM. Or we could just say, DRAM sucks, and we want to replace it with PCM. How can we do that? Well, at first glance, that sounds like maybe a bad idea because we just talked about all of these things that make PCM really difficult to use. But we'll see there have actually been people that have done this and have found interesting ways of making it perform like a DRAM main memory. So how do we mitigate some of the shortcomings of that device, and how do we minimize the amount of DRAM in the system are also important research challenges that we want to look into. And how do we take advantage of the fact that it's byte addressable and fast, non-volatile memory? Remember when we were talking about virtual memory? We had this problem of disk drives are the most efficient when you can read a large amount of data from the device. Non-volatile memory is persistent like a disk drive, but it doesn't have this limitation. You can actually say, I want the byte at physical address 0x blah, 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 and it will give you just a cache block or a chunk of data, not a huge amount of data that was read from memory, like in a disk. So how can we actually use that in applications? And here's a key thing that's underlining all of this work that I alluded to earlier, which is can we design new architectures that don't depend on the underlying non-volatile memory device that's being used? This is really important from a research perspective because we don't know, what systems are going to adopt as the de facto non-volatile memory device. Maybe they'll use a lot of different devices. Maybe there will be a very heterogeneous main memory that's composed of different things. We don't want to limit ourselves to just one specific device. And I would argue that these questions they don't just apply to if you're doing research in this area. I think even if you're on the job, if you're basically, let's say you're working at Intel, and Intel comes to you and says, we're looking at these devices, they're starting to become reasonable. We want you to figure out how can we start to use these in the system. Let's look at the main memory, let's start there, and we can expand our search. These are the type of questions that you want to be asking yourself when you're sort of exploring different design alternatives. OK, so sort of tackling the first question head on, how should PCM-based main memory be organized? We talked about 3 different ways that are pictorially demonstrated here. The first one, so starting from the left, we have today's system. We have a CPU. We have this block that says MC. That's the memory controller that you've been implementing. And it's connected to a bus, and it addresses a bunch of DRAM. Cool. Low capacity, though. So moving toward this middle drawing in the figure, you can see that we've replaced some of the DRAM with phase change memory. What this has the effect of is now we have a lot larger effective main memory, but some of it is a lot slower and has different characteristics than another portion of it. Okay? The most extreme case is all the way on the right, which is we just replaced everything in the main memory with PCM. Like I said, you'd think that would be slow, but we'll look at some interesting ways of making that work. So some people have initially looked at some hybrid PCM and DRAM main memories, and the key question there was, how do we partition data between these two devices, right? Because you used to just have this virtual address space that mapped to a physical address space that was homogeneous. All of the pages in your physical address space behaved in the same predictable way. Now, we have this problem of you have a virtual address space that's still mapping to a physical address space, but some of the pages in this physical address space are really different when you access them compared to some other ones. How do you actually reconcile that? OK, so if we look at this scenario, which we'll call a hybrid memory system, it's a hybrid of DRAM and some non-volatile memory, here are some challenges there. Partitioning. So how do we want to use the DRAM? Should we use it as a cache? Should we use it in the main memory itself? Is it in the physical address space? Or should we make it configurable? Maybe the OS can say, I want 1 GB of DRAM. That's just a reserved cache for phase change memory. And I want 15 GB of DRAM to just be used for, I don't know, I want to use it myself as the OS. What fraction, how many memory controllers do we even have, right? Because these devices have different memory timings. And as you all know by now, you have to get, those timings are associated with some sort of control logic. And if we have different timings, can we even use one memory controller to manage both types of devices? We could, but it would make it more complex. Does it make sense to have multiple of them? Data allocation and movement, so in terms of energy, performance, and lifetime. Who's managing where data is placed on these devices or managing how data is being moved between these devices? What are good algorithms for moving this data? Do we want to use like a page table type or a virtual memory type algorithm where it's just kind of like a clock algorithm or least recently used? We're just putting things into DRAM and occasionally removing things that weren't used recently? Maybe. Maybe there's more complex things that we can do because the benefit is even greater. How do we prevent degradation of service due to wear out? So if a PCM cell fails, which inevitably it will, how do we handle that gracefully so that we don't just get some sort of kernel panic and our system crashes? Do we deal with that at the software level, at the hardware level, or a combination of the two? How do we redesign the cache hierarchy, memory controller's operating system, to mitigate PCM shortcomings and use its advantages? And how do we even design the chips themselves and how they're connected to one another? Maybe we want to rethink the design of systems that incorporate these two devices because they have new requirements. OK, so that was looking at the hybrid memory side of things. What about using it as a main memory? So people have also looked into this. And basically, you could, in theory, replace all of the memory in your system with PCM. And we'll see the techniques that they use to overcome all of its shortcomings. So first of all, let's talk about what I just mentioned, using phase change memory as a complete replacement to DRAM. How does that actually work? So here is an initial study that Professor Mutlu worked on with some of his colleagues. And what they did was, like we said, they first surveyed a bunch of different devices to try and figure out what is the nature of PCM so that we can actually incorporate that into our simulators and model it accurately. And then they kind of found some average parameters. These are the parameters. That's cool. Here's what I think is interesting. So if you were to just naively replace DRAM with phase change memory, what would happen? Well, here's what would happen. You would have 1.6x the delay, so suddenly your main memory just got almost twice as long to access. You would have 2.2 times the energy, so you need a bigger power supply, you're drawing more power now. And guess what? You have a 500-hour average lifetime if you use phase change memory, and you just start running applications and your OS kernel on it. I don't know about you, but I I would reach that limit really, really, really quickly. So this is an obvious problem. And this was sort of a straw man example that they came up with just to illustrate the downsides of just naively replacing DRAM with phase change memory. But I think this is really good motivation for why, as an architect, we want to sort of figure out how to redesign the system. I guess a non-engineer would sort of look at these results and say, OK, no way we're replacing everything with non-volatile memory. But let's take a look at what we can potentially do. So this paper proposed a couple of different ideas that I'll go over right now to help deal with these shortcomings. So the first idea was to use, instead of using one big row buffer like DRAM uses to buffer data that's read from the cells, what they proposed doing was using multiple narrow row buffers. So think of taking that same row buffer circuitry, chopping it up into maybe 16 pieces, and being able to operate them independently. Why is this good? Well, it reduces the number of array reads and writes. Why is this the case? Because in DRAM, when we read something into the row buffer, if it's a huge row buffer, we're reading a lot of data, and then we're writing a lot of data back when we eventually store the data back into the device. If we have multiple small row buffers, we're still loading a lot of data, which is really energy intensive. We don't have to write it all back unless it changed, because remember, it's non-volatile. So we don't have that problem like DRAM. But if we have tiny row buffers, then we only have to read a little bit of data, the data that we're really interested in. And that saves a lot in terms of power and even latency. And this can help improve endurance, latency, and energy. And the other idea that they proposed was to only write into the array at the cache block or word granularity. So instead of writing back a bunch of data, or even if you read out like a fraction of the DRAM row buffer size, don't write all of it back unless it's dirty. And furthermore, try and write back only the smallest amount possible that you need to reflect those updates in the phase change memory. So they wrote back at a small granularity. That has two benefits. One that's not listed here is it reduces the energy consumption that would be required, and it also reduces wear. You can think of it this way. It's like you have a bunch of phase change memory. If you keep writing back things at a large granularity, sort of those, if you can think of each cell as having a little counter of how many times it's been written to, if you're needlessly writing back data, you're increasing that counter. You're decreasing the time before that cell fails. If you write back just a little tiny amount of data, you're not increasing as many cells as counters. On average, you're going to have longer device lifetimes. That's great. So if you combine these two simple, relatively simple in hindsight techniques together, what happens? Well, now in our system, remember that uses no DRAM whatsoever, we can get 1.2x the delay of an all DRAM system. I think that's pretty impressive. We also get that at the same amount of energy consumption, even better, and a 5.6-year average lifetime. Cool. And we talked about this before, but PCM is expected to scale more and more and more. And all of these benefits, guess what? They get even better when you start scaling the device. So that's great. A couple of caveats here. One, if you have a worst case access pattern, let's say you know the device layout, you know the wear leveling algorithms, you know everything that's going on in the system, you could come up with an attack that actually exploits this system and causes a really, really short lifetime once again. Now, this in turn has spawned off a bunch of different research into wear leveling algorithms geared specifically toward phase change memory. So they have to be low overhead because we're dealing with DRAM, not flash here. And they also have to be effective at improving lifetime. So in fact, even this caveat isn't as bad as you might think. The other one is that intensive applications can see a pretty large hit in terms of performance and energy. Remember, we're not buffering as much data at a time. So if you think of an application that actually accessed a lot of data from the row buffer at one point in time and also wrote a lot of data back to memory, they're still going to have those, they're still going to see the effects of the PCM in the system. But in terms of average performance, we're doing kind of good. The other question that many people have asked about this paper is, were their assumptions reasonable? I think at the time, based on the devices that they looked at, these were some reasonable assumptions. Nowadays, devices have evolved. These technology parameters in some cases could have gotten better. In others, when they've actually started to integrate a bunch of these devices into the same technology, they could have gotten worse. So maybe it's time to reevaluate those. OK, so that was one option, which is just replace DRAM with PCM. What if we combine the two technologies together? Let's see what we can do here. So here's a hybrid memory system that we talked about from before. We have a CPU up here that has two different memory controllers. But remember, it doesn't necessarily have to be two. We could get away with just one complex memory controller. One of them is interfacing with DRAM. And DRAM is fast. And it's durable in terms of cell lifetime, not in terms of data storage. But it's small in terms of capacity. It's leaky in terms of charge. It's volatile. And it's high cost per bit. In addition, this other memory controller interfaces with phase change memory, or pick your favorite non-volatile memory. And it's really large, non-volatile, low cost, but it's slow, wears out, and has high active energy. I don't know about you, but when I look at this sort of system, or when I started to look at this system a while back, you can kind of start to see that these devices really complement each other. Where one of the devices has deficiencies, the other one actually has benefits that can help make up for them. So the question is, how can we get the best of both of these devices? And at a really high lifetime. So one option of using both of these devices in the same system is to use DRAM just as a cache for phase change memory. So in this case, PCM is the main memory, and DRAM just caches rows of PCM or blocks. So let's take a look at, or we will take a look at what this architecture looks like. You can imagine some of the benefits from this system is if your data is located in DRAM, that's great. You can just access it from DRAM and you get the main memory latency that you've been used to. And here's another benefit. If you're writing a lot of data and it has locality in the DRAM cache, you can actually filter a lot of writes that would have otherwise gone to PCM. So if you're writing to a specific block, the DRAM can actually capture all of those writes. And when the block gets evicted, then it just performs one write back to PCM. I'll use block and row interchangeably, because really it's just a matter of how much data do you want to bring from PCM into DRAM each time. So in this case, the memory controller hardware is the one that manages the DRAM cache. The benefit is the OS. It is oblivious to this. The OS hopefully just sees main memory access latencies, DRAM access latencies at PCM capacity. That's the hope. But there's really three issues that can potentially, and potentially more, that are going on in the system. One is, what data do we place in DRAM? What's the granularity that we move data at? And how do we design a low-cost and hardware-managed cache? Because we're adding hardware now if we're using it like a cache. So I'll go over two different idea directions that we've looked at. One is locality-aware data placement, and the other is cheap tag stores and dynamic migration granularity, dynamic movement of data between the granularity between PCM and DRAM. So first, let's look at row locality-aware data placement. You guys know what row locality is by now, right? It's basically how much data is being accessed by a program from the row buffer. Row locality is good in any main memory device because the row buffer can be accessed really quickly. So here's the system that we'll be looking at. Kind of the same system from before, but now we're zooming in a little bit into these blocks. We have the CPU, the memory controllers, and a DRAM cache to a phase change memory, main memory. And within each of these, they still have banks. So DRAM has banks, and PCM has banks, just like DRAM. They're organized in a similar way. This is for cost efficiency reasons. And within these banks, both devices have row buffers, like we talked about. And this row buffer circuitry, it's the same, whether you access DRAM or PCM. It's not tied to the underlying cells that are in the chips themselves. So a row buffer hit has the same latency regardless of whether you're accessing data from DRAM or PCM, and a row buffer miss has small latency in DRAM, because DRAM cells are faster to access, and large latency in PCM. So what does this mean? If you have a row hit in the DRAM cache, it's just as fast to service as if you have a row hit in PCM. If you have a row miss in DRAM, it's a lot faster to service than having a row miss in PCM. So what can we do with this interesting symmetry and asymmetry provided by the row buffers? Well, accessing the row buffer in PCM is fast, and what really incurs a high latency in the PCM access is a row buffer miss. So we'll try and avoid this. Here's the key idea. We want to cache data in DRAM that frequently causes row buffer conflicts or misses. So if data, when we go to access it frequently, is not in the row buffer, let's try and place that in DRAM. And we also want to cache data that's reused many times, because then we'll just get multiplicative benefits by putting it in DRAM. And this reduces cache pollution, and also it doesn't waste bandwidth on data that's just accessed once and then never accessed again. So here's sort of the simplified high-level rule of thumb that you'd want to follow in this type of system. For streaming accesses, if you're just streaming through data in the row buffer, let's leave it on PCM, because for most of those accesses, we'll just be accessing the row buffer. It'll be really fast. For other accesses that have some reuse, let's cache those in DRAM, and we can access them hopefully a lot more quickly than if we were accessing them from PCM. And what we'll see is this can actually bridge half of the performance gap between all DRAM and all PCM memory for memory-intensive workloads. Now, half the gap is actually pretty nice, because remember, PCM is actually many times slower than DRAM in some cases. So we're getting pretty close. So the idea here is for a subset of rows in phase change memory, what we want to do is we want to track some statistics, because we have to determine which data to cache. So we're going to track some statistics here. One is the number of row conflicts that data has received, and we'll use this to predict future locality. So the key idea here is if we've seen a bunch of row misses in the past when accessing this data, we're going to predict that we'll continue to see row misses when we access it in the future. And we also track the number of accesses as a predictor of future reuse. So if we've accessed this data a lot of times in the last however many cycles, we predict that we'll continue to access it. These are just predictions. Occasionally they'll be wrong, and we'll cache some data that we didn't need to. That's OK, though, as long as most of the time they're accurate. The policy then is we cache a row in DRAM if its row conflict and access counts are greater than some threshold. Simple, right? We just check. Whenever I've gone to access this data, I've missed in the row buffer the last 10 times. And if a threshold is like 8, then we say, OK, I satisfied the locality characteristic. And if maybe we say, OK, I've accessed this row in total 20 times, and our threshold is 15, we say, OK, I've satisfied the number of the reuse characteristic. So what does this mean? This data is reused very heavily, and whenever I reuse it, I have to miss in the row buffer and go to the actual cell. So in this case, we actually want to move that data into the DRAM cache. And so this relies on different thresholds for figuring out locality and reuse characteristics. One size might not fit all workloads, though. So you can imagine dynamically adjusting these thresholds based on the characteristics of the application. And this is something we looked into. We can use a simple cost-benefit analysis every now and then to figure out, am I wasting too much bandwidth moving all this data around, and am I actually getting benefit from data that's being accessed in the DRAM cache? OK, these are just some evaluation information. The main thing to note here is the way that we've modeled the row buffer. So we have some latency for a row buffer hit, which is the same across both devices. That's shown in the top blue line. And we have a row buffer miss latency, which is twice as long as DRAM, and quite a bit longer in PCM, depending on whether the row buffer has a clean contents, in which case we don't have to write it back, or whether it has a dirty contents, in which case we actually have to start heating up those cells and changing the data. And we're caching data at the row granularity. So 2 kilobytes of data are traveling across the system into the DRAM cache. Just to give you a feel for what this can potentially do, so here we have a few different workloads. There's server workloads. These are things that are relatively memory intensive. They're running on big servers like IBM might have or Oracle. There's some cloud workloads. So these are things that you might see in a consolidated cloud environment. And then there's an average of the workloads. And that's on the x-axis. On the y-axis, we're looking at a performance metric. In this case, something called normalized weighted speedup. Higher is better. There's 3 different policies that I'll show here. The leftmost bar is a caching policy that's just reuse aware. So if you were to just track how frequently used is this data and just cache data that's really frequently used, that's that performance. The middle bar is row buffer locality aware. So this is if you just tracked, how frequently am I missing in the row buffer and cache that data, that's that bar. And the rightmost bar is if you adjust these thresholds for how much am I missing in the row buffer, how frequently am I accessing data dynamically to suit the workload. And you can see that it's possible to get a lot more performance benefit. And this is just looking at performance. So we can also reason about these in terms of different metrics. So there's really 3 benefits that are going on here. The first one that leads to increased performance is we're actually increasing. So these are a bit non-intuitive, and I'll try and step through them. The first benefit is that we're actually increasing row buffer locality in the phase change memory compared to the baseline system. Why is this the case? Because what we're doing is it's kind of like we've identified the data that has bad row buffer locality, and it's like we have a big net, and we're grabbing up all of this data, and we're dumping it in DRAM. And what's left, the accesses that are left that go to non-volatile memory are the ones that have high row buffer locality. So overall, the accesses that are going to phase change memory have high row buffer locality, which is really good. They don't have these little spurious accesses in between them that are changing the row buffer and causing conflicts. The second benefit is we reduce memory bandwidth consumption because we're actually filtering out some data that's being cached. Instead of just using a policy that doesn't do any sort of filtering and just blindly moves data from phase change memory into DRAM, what we're doing is we're actively saying, unlike a traditional cache, I'm making the decision to not cache some data. I'm just going to leave it in phase change memory because it doesn't have properties that I like. The indirect benefit that this provides is when I make the decision to leave data in phase change memory, I don't have to move it all across the bus and disrupt accesses that could have been using the bus at that point in time. The third benefit is that we actually are able to balance the request load between DRAM and PCM. This is a bit subtle. If you think about DRAM and PCM as sort of these memory devices that are residing side by side, we could end up with a scenario where if all of the accesses in our workload have good locality, we might cache all of their data in the DRAM cache, and they would all access their data from DRAM. Now, at first, this seems like it would be a good idea, right? Because everything running on the system is mainly accessing DRAM. Here's the problem. We actually have 2 buses in our system. One bus is connected to DRAM. The other bus is connected to PCM. If all of your accesses go to one device or the other, you're effectively only using one of the buses in your system. So if you can find a way to spread the accesses across both of the devices, and therefore both of the buses, you can actually get a lot more parallelism in the system than if everything was just all going to one device. And by filtering out some of the data that's being cached, some data with high locality can still remain on PCM, and accesses will continue to go to PCM, and that'll balance the load better. OK, so this is just looking at if we have a DRAM cache with phase change memory and the locality-aware placement on a 16-core system, compared to using all PCM, we can get 14% better performance. So this is good. We've achieved a lot better performance than just replacing the system with PCM. Compared to all DRAM, we can get within 29% of the performance. That's still really good because the native latencies of PCM versus DRAM are actually, remember, 4 to 12x, something like that. Oops. And, oh, OK, I guess that was it. Yes, so that's row buffer locality-aware data placement. Let's look at one final technique that we can use to leverage non-volatile memories, and then we'll get out of here. OK, so we just talked about a system that used a large DRAM cache to cache PCM data. What we didn't talk about, and what I sidestepped over, is the fact that we're using this DRAM as a cache. And what does a cache need in order to locate its data? Well, it needs some sort of tag storage. Do you remember when we looked at caches? We have certain bits in the address that are used to tag data. And those bits actually have to be stored somewhere. DRAM is no exception. And DRAM, in fact, exacerbates this problem because it's a huge cache, so we have to store a lot of tag data and associated metadata. For example, LRU counters for every, say, cache block in the DRAM cache. So we'd like to use a lot of DRAM for the reasons that I just described, but there's reasons why it's difficult to use it as a cache. We have tag and block-based information like age information. So the question that we then wanted to ask was, how do we design an efficient DRAM cache? So here's looking at the same system as before. And in this typical system, just to put everything into perspective, we'll have a load from the processor. And we're going to need to look at some metadata that's probably in the memory controller that tells us where this data is located. Do I find the tag for this data in my tag store? If so, then I want to access the data from DRAM. In this case, we found it in DRAM, so we'll actually perform the access and then transfer the data across the bus. OK. What's the problem with this system? Well, even though it's just shown as this sort of gray bubble here, that metadata can actually get really, really big, especially when you start to look at DRAM caches that are, say, 8 gigabytes in size or larger. The metadata can easily approach the size of a last level cache in the processor, and it's made of the same basic cells, SRAM. So do you really, what would you rather do? Would you rather have a big DRAM cache and half of the potential last level cache size that you could have? Or would you rather just not use DRAM at all and use more and have more cache space in your system? So this is kind of a conundrum, right? It's like the designer now has to make this decision about where do I want to use these SRAM cells. So what we wanted to try and do is take SRAM out of the picture as much as possible. And here's how we did it. The first idea that we'll look at is storing tags in memory. So here's the idea. Before, you stored all of your tags in this SRAM structure. And whenever you had an access, you would go to this SRAM structure, you would look up the tag data, and you would say, OK, it's in DRAM, or it's not in DRAM. What if we took that same tag data and we distributed it across main memory? Same amount of storage, same tags. It's just now it's in the memory itself. This is kind of a weird concept because we're blending the storage substrate and the data that manages the storage substrate all into one. But it's possible to do. The idea is to store the metadata in the same row as their data. So here we have the example of we have a DRAM row, and we have some cache blocks that are in this row. And at the end of the row are some tags and maybe LRU data that actually maps to the cache blocks that are in this row. So tag 0 stores the tag for cache block 0. Tag 1 stores the tag for cache block 1, and so on. And now, when we access main memory, because it's all in the same row, and we access one row at a time, we bring in the data and the tags for the data simultaneously. So this is good because now we completely eliminated any on-chip storage overhead. We don't have this conundrum anymore of where am I going to use my SRAM. The problem is now we don't have SRAM, right? So SRAM is great because it's fast, but now we actually have to access DRAM before we can even determine if some data is cached. So that seems pretty bad. And also, if we actually hit in the DRAM cache, one access just became two, because we first have to go to the DRAM, access the tag data, go back to the memory controller, check is the tag for the address stored in DRAM, and then go all the way back to DRAM and access the data from the row. Now, it could be worse because we're actually accessing data from the row buffer, so we get a little bit of a benefit there, but still, 2 accesses compared to 1. Here's the second idea that sort of alleviates that problem, as you'll see. Right now, what we're doing is we're storing metadata in DRAM, and this is to reduce the metadata storage overhead, that large SRAM structure. But what if we use a little bit of SRAM? Not a last level cache size, but just a little bit. And here's how we're going to use it. We'll actually cache metadata on the memory controller. We won't cache data, but we will cache metadata. Why is this good? Because now we're using only a small amount of DRAM. And if our data that we're accessing has good locality, if we're always checking the same set of tags within a small amount of time, we get the same exact performance as if we had a huge SRAM cache, because those tags are always being stored in this small amount of SRAM, and they're being accessed at that same latency. There's a third idea that is enabled once you start to store data at these different granularities in the cache, which is dynamic data transfer granularity. So as you can imagine, some applications can benefit from caching more data at a time. This is kind of like thinking about prefetching. If you have a streaming access pattern, you might benefit from moving a large amount of data into the cache compared to if you have more of a random access pattern, where you're just accessing a block here, a block there. So the idea is, so if an application has good spatial locality, that's great. We'll cache more data. Some applications don't have a good access patterns for spatial locality. And so if we were to move the data at a row granularity, like we did previously, remember in the previous work we were moving data in big 2 kilobyte chunks? If we tried to do that for data that has not good spatial locality, will actually hurt performance because we're just moving it all across the bus to access one cache block. So the idea that we came up with is to use a simple dynamic caching granularity policy. So basically try and figure out on a per application basis, how much data do you want to move around? And again, we rely on cost-benefit analysis to figure out what's a good DRAM cache block size. And we look at a couple of key things. We first group main memory into sets of rows. So you can think of taking the main memory, which I'll draw here as a bunch of different, maybe we have a few banks in our system. And if I were to just divide this main memory into a couple of different sets, let's say that all of the rows here are set 1, all of the rows here are set 2, all of the rows here are set 3, and all of the rows here are set 4. What we can do is we can follow a fixed granularity for certain of these sets. So let's say we'll call them kind of like tester sets. These are just sets that maybe in set 1, let's say migrate at 64 bytes. And let's say set 2 is migrate at 2 kilobytes. So we have a couple of sets that we put aside, and we're just going to do these blindly, essentially. And then all the rest of the sets in main memory, we can actually control. For all of these, we'll do migrate at x. And we can change x at runtime per thread. And I'll show you how this works. we can basically sample each of those static sets, those tester sets, to figure out what is a good granularity for this system. Is it more towards smaller cache blocks, larger cache blocks? And then once we sample that migration granularity that works really well, we can then apply that to all of the rest of the sets for a certain amount of time. And hopefully that gives us better performance than if we were to just use one policy statically throughout all time. So what we're basically doing to figure out this information is we compare the average access latency within these sets versus the amount of data that they've cached. So the cost of caching at a large granularity is moving a bunch of data across the bus. The benefit is you get potentially better average memory access latency. If we look at these two values and compare them, we can pick, for each of these tester sets, we can pick the one that has the most benefit for the least cost. And we do this every quantum. Simple. OK, so tying everything together. So this was called Timber. It stands for Tag and Memory Buffer. And it stores recently used tags in a small amount of SRAM. That's what we went over. So the device itself is just this tiny buffer, this tiny amount of SRAM. And it caches these tags. And even though it's caching metadata, it's still a cache itself, except what we're storing is metadata. So the tag and memory buffer has tags as well, and these tags are the row IDs whose metadata is cached. So it's just like a cache, but just for metadata. And so when we have a particular load, we can look in this buffer to see if its row's metadata is buffered, and we can compare the tag and instantly figure out where the data is located. So if it's cached in this structure, we don't need to access DRAM twice. We access it once, just like before. And a cache hit is determined quickly. This is good because a cache hit is the type of access that we want to try and optimize for, because we want the lowest latency. So let's just go through an example here. If we have a load from memory, now we have this structure called the Timber. And in the Timber, we can check, is this data located in DRAM? Is it not? Is its metadata not cached? Do we need to fetch it? So in this case, it's in DRAM, so we can just access it from DRAM. That's great, just like before. Here's what happens if its metadata isn't cached, though. So we have another load, and we realize that we don't have the row metadata for this row cached. Uh-oh. Well, first we have to access the metadata for this row and cache it in the Timber. So here we go. We're accessing the metadata block. We bring it back to the memory controller, and we cache it in Timber. We update everything. We update the tag. We update the data, which is the metadata for that row. And now that we have the metadata, we can check. We can see, is this data actually located in DRAM? Is it actually located in non-volatile memory? If at this point it's located in DRAM, cool. We already brought the row into the row buffer when we accessed its metadata. We get a row buffer hit. We can bring the data back and service the request. Great. So just some quick results on how this actually works. If we look at different techniques, so here we have an all SRAM system. This is the system that I talked about before, that's where you basically just have a conventional cache tag store implemented in SRAM. That's really big, really power hungry. We kind of don't want to use that. This is a technique which is kind of a first step that some people had looked at before, which is let's take the tags, let's take the metadata, and let's put it all in one contiguous physical region in DRAM. So not in the same row as the data, but just in some block of DRAM that's kind of set aside, maybe in one bank, maybe across multiple banks striped, but not in the same row. Oh dear, these are like, it's autopilot. OK, so that's region. Tim is just tags in memory. This is if you just store them and you don't buffer them. And Timber is that tiny little buffer that's added on that buffers the recently accessed tags. Same performance metric on the y-axis, normalized weighted speedup. OK, so the downside of storing tags in just a contiguous region of memory is that you basically have to incur 2 row buffer misses every time you want to access a block that's cached. One to access the metadata, the other to access the data itself. Really degrades performance. The benefit of storing the tags in the same row as their data is you increase row locality. Great. That reduces average memory access latency. And the benefits of caching some of the tags in a small buffer is that if you have data with good locality, now it just sees the DRAM as if it was in the ideal case, which is that it basically has SRAM access latency to figure out if some data is cached or not. In terms of, so here's our technique that does that dynamic caching granularity based on the cost-benefit analysis. What you can see is that we can increasingly improve performance because what we're doing here is we're reducing channel contention and improving spatial locality on a per workload basis. So we don't always move things at the same granularity, and that improves across different workloads. So we can actually, interestingly enough, get within 6% of that ideal case, within 6% of using a 32 megabyte SRAM tag store, which is the size of a large last level cache. Cool. In terms of energy efficiency, we can even do better than the baseline case because when we're migrating data with the dynamic technique at a smaller granularity, those are less electrons that we have to move across the bus in the system compared to the baseline. So this is good because now we can save energy for different types of workloads. OK, let's just kind of tie it all back together with one main slide. Remember at the beginning of the course, first lecture, we talked about these different levels of abstractions, these different basically ways that we can view the different portions of a system. We start with a problem, we translate it into algorithms, we write some programs, we have a runtime system, all of these things. And many issues and ideas so there's a lot of different issues and ideas pertaining to non-volatile memory that cross a bunch of these different layers. For example, enabling NVM and hybrid memory technologies, how do we tolerate errors? Is this the programmer's job? Is this the operating system's job, the VM's job? That's a good question. How do we enable secure operation of these devices? How do we prevent against an attacker just wearing out the device that you're using and causing it to be inoperable? How do we tolerate performance and power shortcomings? We started to look at some works that use different types of caching to target those. And how do we minimize cost? So memory is a very cost-driven industry. We always want to have low cost per bit. And how can we exploit these new technologies? I suggested some options during the course of this lecture, but I think these are a bunch of still open questions. How do we exploit the non-volatility of these devices to deliver better application performance or reliability? I gave the database example, but you guys can probably come up with even more compelling examples than that. How do we minimize energy consumption? So these devices have really high energy writes and even some read operations. How can we limit the effect that will actually affect system designs, especially if we're running this in a system with thousands and thousands of servers? And how can we exploit non-volatile memory on the processor chip itself? Think about the potential that we could unlock if we could take these high-density memory technologies and put them on the processor. So now your last level cache just became 16 gigabytes in size. Can we do that? And we might start to see some techniques that are looking at these. And these are all active memory, active areas of research that people are looking into. Just to quickly go over security challenges before we wrap up. So we talked about earlier on endurance limitations of these devices. So they're vulnerable to these wear-out attacks. In addition, they're non-volatile, so their data stays around after we turn them off. Think about the RAM in your system. If I'm writing a program, and let's say it's buffering some password, even if it's an encrypted password. Let's say I allocate a buffer in memory, and I store your password that you input in that buffer. When you turn off the system, you'd expect that password buffer to go away, right? It's like as soon as you reboot and restart the program, it's gone. Interestingly enough, actually, this is a side note, but there have been some security papers where they've actually powered down a computer, quickly taken the DIMMs out and put them in liquid nitrogen, right? So now charge is going to leak more slowly, very, 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 very cold. Taken them out, put them in another system, and forensically analyzed those DIMMs. And they have been able to read data off of them after doing that process. And you can imagine that at those temperatures, it takes about minutes to even tens of minutes before all the charge will leak. That's kind of an extreme attack vector, but in non-volatile memory, that's the norm. As soon as you power off your device, anything that was in non-volatile memory, be it a password buffer or your shadow file for passwords in Unix, is going to stay there. How do we manage that? How do we secure that? Do we encrypt everything on non-volatile memory? I guess we could, but then we need special hardware to decrypt it, and we're increasing the cost and latency of accessing that device. Also, with multiple bits per cell, this is kind of a sneaky attack. But if you're storing multiple bits per cell, and your operating system, let's say for some reason your operating system allocates you a page. Let me draw a picture. This will make more sense. If you're storing multiple bits per cell, this is basically what the organization in your memory looks like. If you have a row of cells, let's zoom into one of these chips right here and make it really big right here. So this is a row of cells. In multiple bit technologies, instead of just having like 1, 0, 1, what you actually have is you have this sort of organization where you have multiple bits that are being used in each cell. These are cells. And the operating system can map a page to this lane of cells and another page to this lane of cells. What happens if this is like a protected OS page and this is your random page that you got when you issued a malloc? Well, if accessing, say, both of these pages was completely isolated from one another, if there were no discernible effects when you access this bit versus this bit, maybe there wouldn't be a problem. Here's the problem that I'll tell you about. Because of how these values are stored and because of how they're sensed, the latency of accessing this 1 next to this 0 will be different than if you access this 1 next to a 1 that's in that position. This is a side channel that you could potentially exploit based on just reading the contents of these cells that you have access to, what the contents of the other cells that are adjacent to them is. Multi-level cell flash actually suffers from this same problem, and people have exploited this vulnerability, or at least shown that it's exploitable in actual hardware. Interesting things to worry about, I guess. So we can solve some of these problems by architecting better memory chips to avoid wear-out attacks, or hybrid memory systems where we use DRAM to buffer some writes, and also detecting whether attacks are occurring online and mitigating them at the source. We can use, like I said, encryption, decryption of the whole main memory. Maybe that's overkill. Maybe there's a way of managing data in a hybrid memory that can actually get around this limitation. Maybe you put privileged data in DRAM, so when you actually do power it off, it's gone. OK, so we talked about some major trends affecting main memory. I hope I've convinced you that main memory scaling is going to become a bottleneck, if not already, and that we need to take some initiative to prevent that from happening. We talked about some of the requirements for an ideal main memory system, and then we dove down into how can we exploit these new technologies to get closer to that ideal. And we looked at a few concrete examples of how we mitigated some of their downsides to make them more like that ideal memory system. Went over some background and looked at 2 specific techniques. So with that, lectures for the course are officially adjourned. I'll continue to see you in labs and the review sessions, but I really hope you've enjoyed this course. I know I and the other TAs have really enjoyed teaching it, and do consider taking 740 if you find that this is material that actually interests you and you'd be that you want to continue learning about. So thank you for all of your attendance throughout the course, and good luck on the upcoming lab and final. So yeah, thanks.